Beneath the glittering surface of the ocean lies another world, a world that is silent, endless, and crushing. Here, sunlight slowly fades into complete darkness. The water grows colder, and the pressure becomes so intense it can bend steel like paper. Yet in this frozen, lightless abyss, life doesn't just survive, it transforms. Creatures that should be small become impossibly large. A shrimp grows as long as your forearm. A jellyfish expands wider than a house. And somewhere in the darkness, a squid may stretch as long as a school bus. This strange and unsettling pattern has a name: Deep Sea Gigantism. Scientists have studied it for decades, but even today, no one fully understands why the deep ocean seems to favor giants. Is it the cold, the pressure, the darkness, or something deeper? Something written into the very rules of how life adapts when pushed to its absolute limits. Today, we're diving into one of the ocean's greatest mysteries. Not just to meet these giants, but to understand why they exist. Giants of the deep are real. Deep sea gigantism isn't a myth or an exaggeration. It's a documented biological pattern seen in many species living below 1,000 meters. Take the giant isopod. If you've ever seen a pill bug, the tiny creature that rolls into a ball, imagine that same animal, but the size of a small dog. Bathynomus giganteus can grow over 50 centimeters long and weigh more than a kilogram. It crawls across the abyssal plains like a living tank, feeding on whatever scraps drift down from above. Then there's the Japanese spider crab. With legs spanning nearly 4 meters from claw to claw, it's the largest arthropod on Earth. It moves slowly across the seafloor, looking less like an animal and more like a machine from another era. In open water, we encounter the colossal squid, a creature so elusive we've only seen a handful of specimens. It's believed to be the largest invertebrate alive, with eyes the size of basketballs, the biggest eyes in the animal kingdom. In total darkness, bigger eyes means survival. Even tiny amphipods, shrimp-like crustaceans barely a centimeter long near the surface, grow to over 30 centimeters in the Mariana Trench. They swarm the seafloor, scavenging anything that falls from above. And jellyfish follow the same pattern. The big red jellyfish drifts through the deep with a bell more than a meter wide. No tentacles, only thick, fleshy arms. Slow, ghostly, massive. At hydrothermal vents, giant tube worms grow over 2 meters long, surviving without mouths or stomachs by farming bacteria inside their bodies. These aren't exceptions. They're a pattern: cold, pressure, and the physics of size. So why does the deep ocean create giants? The first answer lies in temperature. Deep sea waters hover just above freezing, rarely rising above 4 degrees Celsius. Cold slows metabolism. Chemical reactions happen more slowly. Energy is burned at a much lower rate. In a place where food is scarce, this is an advantage. A slower metabolism means animals can survive longer without eating. They don't need to hunt constantly. They can wait, and waiting is survival in the abyss. Cold water also holds more oxygen. Larger bodies require more oxygen, and in warm waters, growing too big becomes dangerous. But in the cold depths, oxygen is plentiful, allowing massive bodies to function efficiently. Then there's pressure. At 4,000 meters deep, the pressure exceeds 400 atmospheres, enough to crush a human instantly. But deep sea animals are built for it. Interestingly, larger animals may actually handle pressure better than smaller ones. With a lower surface area to volume ratio, their cells experience less distortion. Size becomes stability. World without food. But physics alone doesn't explain everything. The deep sea is one of the most food-poor environments on Earth. Below 1,000 meters, sunlight disappears. Photosynthesis stops. No plants grow. Life survives on marine snow, tiny fragments of dead plankton, waste and organic debris slowly drifting down from above. By the time it reaches the abyss, most of it is gone. Occasionally, something larger falls, a dead fish, a squid, or a whale. These rare events, called whale falls, can feed entire ecosystems for years. In this world, efficiency is everything. Large animals burn less energy per unit of body mass. A giant isopod can go months, or even over a year, without eating. Size allows them to store energy and endure long famines. They grow slowly. They live long. The Greenland shark, a deep-dwelling species, doesn't reach maturity until around 150 years old and may live over 400 years, the longest-lived vertebrate known. Time moves differently in the deep. Bigger means safer size also offers protection. Deep-sea predators are rare and specialized. There are no great white sharks here, no dolphins, no orcas. Predators like anglerfish and dragonfish rely on ambush, not speed. A giant isopod with thick armor isn't worth the effort. A massive jellyfish,
allowing tissues to support greater mass without suffocating. Then there's pressure. At 4 kilometers down, the ocean presses with a force of over 400 atmospheres. That's like having a dozen elephants standing on every square inch of your body. For us, it would be instant death. But for deep-sea creatures, pressure isn't an obstacle. It's just normal. Interestingly, pressure might actually favor larger body sizes. Smaller animals have a higher surface area to volume ratio, meaning pressure affects their cells more intensely per unit of mass. Larger animals, with more volume relative to their surface, may handle pressure more efficiently. Their cells are less distorted. Their internal structures remain stable. There's also a principle called Bergmann's rule, observed in many cold environment species. Larger bodies retain heat better than smaller ones because they have less surface area per unit of volume. In a freezing abyss, even a slight metabolic advantage from size could mean the difference between survival and death. But metabolism and temperature alone don't explain everything. To understand gigantism fully, we need to look at what these animals eat, and more importantly, how rarely they get to eat it. The deep sea is a desert, not of sand, but of nutrients. In the sunlit surface waters, photosynthesis drives life. Plankton blooms feed fish feed larger predators, and energy flows abundantly. But below 1,000 meters, photosynthesis stops. There are no plants, no constant supply of fresh energy. Instead, the deep relies on scraps.